and we ended up writing the pressure difference across the interface as 2 sigma cos theta by small r. Now you have to remember that this small r is actually this radius of the tube, and in case of the wick it becomes the radius of the pore. So this is important because otherwise the mistake that you can make, anybody can make, is to think that this is the radius of curvature of the surface, but it's not. It's the radius of the tube. And just to illustrate that, I told you that you think about again the cylindrical pore or a tube. You got R1 equal to R2 equal to R, say, which is small r by cos theta. Now what's this? R1 and R2 are the two principal radii of curvature of the surface. And this quantity, which we are calling capital R, is small r by cos theta. Now when you write PC as 2 sigma cos theta by r, this r is again the radius of the pore. Okay. If you write 2 sigma by capital R, okay, then that capital R is actually this quantity. But if you write the maximum this capillary pressure, then that is 2 sigma by r, because the cos theta becomes equal to 1, because theta is equal to 0 in that case, where this surface becomes, this solid line will give you an angle of 0 with this curved surface. Okay, see if that happens. Now up to this we had covered, and now we'll go to something known as heat transfer limitations. So when talking about heat pipes, there are some limitations in the heat pipe. You cannot operate without constraints. There will be some constraints, and so some of these constraints, these limitations can result in heat pipe failure. Okay? And some can lead to heat pipe failure, and some others that need not lead to heat pipe failure. So if you have insufficient liquid flow to the evaporator for a given heat input, that results in a dry out of the evaporator wick structure. So that is understandable. Now these limitations are in these two categories. So there are some which are in the failure category, and there are some others which are in the non-failure category. Non-failure means the heat pipe will not work very well. Failure means the heat pipe will completely fail. It will not work. So let's look at these. First, limitations of non-failure. So there are some viscous limits. So the viscous limit occurs at low operating temperature, where the saturation vapor pressure may be of the same order of magnitude as the pressure drop required to drive the vapor flow. So this gives you insufficient pressure to drive the flow. So you need some pressure drop to drive the vapor, correct? If that is not sufficient, then so there are two kinds of flows we are talking about. There's one flow of vapor through the core of the heat pipe. So if this is the heat pipe, this is the evaporator section, this is the condenser section, then the vapor will flow through the core. So this is vapor, and the central part is called core. Okay. So if you do not have enough pressure to move that vapor, then it doesn't work, the heat pipe performance gets affected. Then there's also something known as sonic limit. If you have low vapor densities, then the mass flow rate, if the vapor density is low, then you have a mass flow rate of vapor. Low density of vapor means high vapor velocities. Okay? And high vapor velocities can result in choked flow. If you know what choking is for compressible flow, that happens. And condenser limit is when you do not have, when you have cooling limitations, such as you have only radiation or natural convection, things like that. So these are the non-failure modes. Now the failure modes will include these three. So there is capillary limitation, entrainment limitation, and boiling limitation. So capillary limitation means that you do not have enough capillary pressure to pump the liquid back to the condenser. Okay. And entrainment limitation means liquid droplets are entrained in the vapor flow and carried back to the condenser. So there is a vapor flow, obviously. So the vapor goes this way. But if the vapor picks up a lot of liquid droplets, then that is also a problem. And boiling limitation is that evaporator heat flux is so high that boiling happens in the evaporator wick. So this whole thing has a wick, evaporator part. If boiling starts happening, then again there is a problem. What you want here is basically evaporation. So it evaporates and you get vapor, and that vapor moves in this way. So the capillary limit relates to the capillary pressure difference. And this is the main point, that the driving capillary pressure is insufficient to provide adequate liquid flow from the condenser to the evaporator. Okay. So if there is not enough liquid flow from condenser to evaporator, then the evaporator will tend to become dry, not getting enough supply of liquid. So capillary limit is the primary maximum heat transport limitation of a heat pipe. So this is something, the capillary limit, we have to understand in some detail. Okay, I have been talking about this, but I had shown you this, but we were talking about only this capillary rise in a tube. But this is an actual scenario of a heat pipe. Now, we'll look at these and we'll try to understand all these quantities. But first of all, we see that the meniscus varies along the length of the heat pipe. Okay, so that you can see from the figure, that you can understand also, because on the left hand side in the evaporator there is evaporation happening, so liquid is moving out, getting converted to vapor. So the curvature there is larger, I mean small radius of curvature out there, right? And on the right hand side in the condenser, you will see that the surface has become more or less flat, I mean somewhat flat on the right hand side condenser. Okay, but in between also there is some variation in the meniscus radius of curvature. Now the point at which the meniscus has a minimum radius of curvature is the dry point. It will be around here, minimum radius of curvature. So that's usually happens in the evaporator, so far from the condenser region. Now on the other hand, on the condenser side, you will have the radius of curvature increasing because the surface is becoming more flat, right? So it's becoming more like this. So that is kind of the wet point. Okay. So wet point is where the vapor pressure and the liquid pressure, these two things are approximately equal. So the difference between the vapor pressure and the liquid pressure is indicated by the radius of curvature. This is the logic that we understood in the previous class. So if the vapor pressure and liquid pressure are kind of equal, then the radius of curvature is actually quite large, and curvature is really small. Okay? So the wet point is kind of in this region, in the condenser region, and the dry point is kind of in the evaporator region. Okay. And this is a figure, both these, this is a figure which shows pressure drops. This is a dry point on the evaporator side, and the wet point is more on the condenser side, close to the condenser side. Now, the pressures of the vapor and the liquid are also shown here. So you will see that by the time it reaches the condenser side, the vapor pressure and the liquid pressure are approximately equal, but towards the end. Okay, again, that is apparent from the radius of curvature. Okay, now we have these things marked like P1, P2, and P4, P3. So this side, so if you get this, don't read too much into the actual curvature I'm drawing here, but just want to tell you that this is 1, this is 2, but on this side, this is not 3, this is 4, and this is 3. So 1, 2, 3, 4. This is the sequence in which we are going. Just a nomenclature. Okay? And you have a capillary pressure difference. The capillary pressure difference has to be able to overcome some pressure drops. So there will be pressure drop in the vapor, there will be pressure drop in the liquid, there are some other kinds of pressure drops which we'll get into, and we are trying to generate the capillary pressure difference which can overcome all other pressure drops so that the liquid moves in the wick, right? That's the idea. So these things, this tells you the meanings of various notations, but we'll come to this little later. Okay. So as of now, delta PCM is the maximum capillary pressure difference generated within the capillary wicking structure. So this is the vapor phase pressure drop. This has got to do with the liquid phase pressure drop, and there are a few others. Okay, now let's go to this figure. So P1 minus P2 is this thing. Okay, how do we know? Because this is kind of like that cylindrical pore which we modeled in the last class. So P1 minus P2 is 2 sigma cos theta e by RCE. Now what is RCE? RCE is the pore radius. It's kind of like the glass tube that we were thinking about. It's that radius, right? It's not the radius of curvature, right? So it's marked properly here, right? So it's 2 sigma cos theta e by RCE. Now P4 minus P3 is 2 sigma cos theta c by RCC. Okay. Now here I don't like the way this has been marked in Lee's book, because the way this has been marked RCC, it appears to be like the radius of curvature, but it's actually not. I mean, what I'm saying is he should have marked it like the way he has marked it in the evaporator section, and he should have shown this as RCC, right? So what is the first C for? Curvature. The second C, condenser. So this side, it is PE, correct? So these two equations we understand. The other thing which we will do is we will say that P1 and P4, they're approximately equal. So there's a P1 here and a P4 here. So we'll say P1 is approximately P4. Okay, these are both in the vapor phase. But just because they're in the vapor phase doesn't mean that they have to have the same pressure, right? But we are saying that in the vapor phase, the pressure drop is small. When it's there, it's non-zero, but it is small. This is the assumption that we are making. Okay? This is the assumption that we are making. P1 equal to P4. And we'll also say that to get the maximum capillary pressure drop, okay, to get the maximum capillary pressure drop, we'll have theta E equal to 0. We are trying to estimate, see, I have the equation written on the top, right? So what is delta PCM? M for C for capillary, okay, capillary pressure drop. M for maximum. M for maximum. We are trying to have an idea of the maximum pressure drop that we can get. Okay. Now, we'll also say that if you look at these two equations, we'll say theta E is 0. To generate the maximum pressure drop, isn't it? Theta E 0 will help, correct? Because then we'll get cos theta E equal to 1. All right. Now we are interested in basically which pressure drop, which number we are trying to get, trying to maximize. There's some pressure drop that we want, isn't it? Driving force that we want. What is the driving force? What is that pressure drop? We want to get sufficient which flow? There are only two things, like vapor flow and liquid flow. Which one? Liquid flow, no? So you have to be louder. Since you are not confident, so you are not being loud. But there's no harm in being loud. Your face is not being shown on the video, so don't worry. Okay. And right, so we want the liquid flow, right? A good amount of liquid flow. That's what we're trying to generate. So we want to. What are the two P's? The difference between P. Which difference we are interested in? P. Tell me which number should I write here? P. P2 minus. No, what is that? P3 minus P2. That's correct. So we want P3 minus P2. Okay. So we can do to get this P3 minus P2, we can do P1 minus P2 so will this work? Yeah, because you're making this assumption. So this will give you P3 minus P2, which we are interested in. We want to see how much, what is the maximum value of this thing, P3 minus P2, that we can generate, right? So P1 minus P2 will be 2 sigma by R CE, the maximum, if we say delta PCM, right? So that will be, I mean, we set cos theta, we set theta E equal to 0, so that we can get 2 sigma by RCE, right? And what about the second term, P4 minus P3? P4 minus P3 is this thing. So we would like to minimize this, isn't it? Because this first term we have maximized. So we like to minimize the second one. So what's the minimum value of this? This will be cos theta C. Okay, theta C can be how much? Theta C. What do you think theta C can be? Theta E we set equal to 0. And theta C? Hmm? Theta C how much? 90. 90. Theta C will set equal to 90. Okay. So then obviously from here, from the second equation, we get 0, right? So this is delta PCM, which is by virtue of this P3 minus P2, which is 2 sigma by RCE. Yes, so this is a maximum thing that you can generate. It's not that you will get exactly this, but this is the maximum that you can generate. Okay. So I have taken these equations from again from Professor Lee's book. So same notations, but I'll tell you where I had a difficulty. So theta E is 0. I told you why. Theta C is pi by 2. So that also I told you why. Now he writes theta C equal to pi by 2. So RCC equal to infinity. That I did not like. So that's why I've cut it like this. Okay. Why do I not like this? Because as I told you, on the condenser side, it's like it's almost like a flat surface. So RCC, he says RCC is infinity, but RCC is a pore radius, so it cannot go to infinity. It's a fixed number, right? If you think about the radius of curvature, that goes to infinity, but that's not the notation for the RCC is not the notation for the radius of curvature. Correct? You understand what I'm saying, isn't it? So that's why I cut it, and it will be on the PPT, and you will see the cutting in the video also. So remember it that way, that just take theta C equal to pi by 2. That's it. Don't consider the other part. Okay. So after all this, we get this thing, which I have already written, and that's this one. Okay, so this gives you an estimate, and you can also calculate individual pressure drops and see. So going back to this, delta PCM, the maximum that you can generate is this thing, correct? So there will be a sigma for the fluid solid combination that you have, from surface tension information. and RC will come from the particular geometry of the wick, right? So you will know how this much you can generate. Now, will that overcome all the terms on the right hand side? Right hand side are those pressure drops against which this capillary pressure, generated capillary pressure has to work, correct? Right. So we'll have to come to this now. What are the different kinds of pressure drops that we can expect? But before that, there is a table in the book. This is table 3.1, which gives you various relations for RC. RC is an effective capillary radius. So I've been just talking about a glass tube, right, so far, because we didn't have a discussion on, let's say, a porous structure like a sintered metal wick or some, you have meshed, wrapped screen wick. So we didn't discuss those things in detail. For those, obviously, we cannot talk about just a pore radius in a very simple way like we talk about glass tube radius. So not that, but there is an effective, the word effective is important, the effective capillary radius for various wick structures. So these are various wick structures. For example, this has got sintered metal. This has got parallel wires. This has got wire screens, various things, right? And for those, there are expressions for the effective capillary radius. Where will you use this? In a problem, you are given some kind of a wick geometry. Maybe you are told that there is a wrapped screen, wire screen sort of thing. Then you calculate RC, which you need here. Okay, you calculate that RC using this thing. So there is a omega, which is the wire spacing. So there are spacing between two wires. Okay, that will come from the mesh geometry, right? That will be part of the information given in the problem. So wire spacing, n is the screen mesh number per inch. Per inch, how many screens you have, and d is the wire diameter. So omega is the wire spacing, small d is the wire diameter. So this sort of information will be given. Then you can calculate RC. Then this sort of thing can be utilized, right? Okay. Now we'll concentrate on the right hand side of that delta PCM equation. So we'll look at individual pressure drops. So this is a vapor pressure drop. Vapor pressure drop is usually small, and we actually neglected it in doing this. But we still have to know how to calculate this one, even if it is small, right? So this unfortunately comes out in the form of some relations which we will not be able to analyze in detail. Okay, so there is some this is delta PV, which is the vapor pressure drop, and this depends on friction factor of the vapor flow. Then it depends on the Reynolds number for vapor. Vapor is flowing in the core of the heat pipe, right? And this is viscosity of the vapor, hydraulic radius of the vapor, etc., etc. There's some constant C also, but this thing you just look this up from book. Okay, when we come to next Thursday's class, then we'll do a problem like this where you just pick up the values and do these calculations, right? Let's also recognize that these are the pressure drops profiles for the vapor and the liquid, and the delta PV. So if the vapor pressure here is PV, here it is something lower. The delta PV is actually quite small, right, compared to a delta PL, which is the pressure drop in the liquid, right? And here pressure drop of the vapor, here pressure drop of the liquid, right? So liquid pressure drop is calculated using this, and again this depends on the heat transfer, this depends on some effective length, and it depends on some wick permeability. Permeability, you know, isn't it? You heard the term permeability. You might have seen a little bit in some porous media discussion. I don't know where you saw permeability. Permeability with the manufacturing. Okay. So this is hydrostatic pressure drop. So this hydrostatic pressure drop is shown for a heat pipe which is at some angle to the horizontal. So that angle which you see is some psi, okay, and this is the diameter dV. dV is the diameter of the vapor core, right? dV is this one, right? And this is psi. Obviously, if this is psi, this is also psi, right? Gravity acting this way, and this angle is psi. Now, this pressure drop can be written like this, using this angle cos psi. This is the normal hydrostatic pressure drop. And similarly, we'll have an axial pressure drop. So what is axial pressure drop? Axial pressure drop obviously is in the axial direction. Normal pressure drop is in the normal direction. And the axial pressure drop will obviously have sine of that same angle psi. Okay, the other one has that cos of psi. Right. So we go to the integrated form of that first long equation that we had seen. And that will have delta PV, delta PL, delta P normal, delta P axial. Okay, all these, so the right hand side, all these terms has to be overcome by the delta P CM that you can generate. Now, delta PV we can neglect because it's typically small. But we still looked at a formula for delta PV. So delta PV will nevertheless calculate. When we do a problem, we'll nevertheless calculate delta PV using that relation. And delta PL will calculate, delta PL will be higher than delta PV. Delta P normal is typically not much, but delta P axial can be somewhat more important. So this is the delta P normal expression. This is the delta P, no, not normal, sorry. This is delta P liquid expression. This is the delta P axial expression. And this one is delta PCM, as we know. And based on this, there can be, see, this has got a Q. What is that Q? Q is the heat transfer. Ultimately, why do you have a heat pipe? To transfer heat, right? And if you change Q, things will change, right? Okay, so you have a heat pipe, and okay, so let this be your heat pipe. This is evaporator, this is condenser. So if you give a lot of heat here, and if you cool down a lot here, then you will tend to transfer a lot of heat, right? But will it work? It might not work, no? For the particular heat pipe that you have, it might not work, because maybe evaporator will get dried up, maybe boiling will start happening, maybe in any case for the liquid and the wick combination that you have, maybe you will not be able to generate that much amount of delta PCM to overcome pressure drop, and all kinds of things can happen. So these are the limitations that we are talking about. This is the physically that's what you should think, that okay, I've got evaporator, I've got condenser, I can generate a delta P, but is that going to be enough, right? This is one way of thinking. The other thinking is that I mean, it's not everything is just pressure drop. It can also be like evaporator running dry, boiling is happening here, sonic limit is reached because you're generating too much vapor, which is giving a very high vapor velocity. Because vapor density is low, you generate a lot of mass flow rate, and that because of that mass flow rate, maybe the vapor density being low, you get very high vapor velocity, so that might choke the flow in all kinds of effects, right? So it's not like you make a heat pipe and it will work under all conditions, obviously not. Okay, the limitations, when we talk about today, we have been talking about limitations basically mean these things, but okay, there are some limits to the way this heat pipe can function. Beyond those parameter ranges, the heat pipe will not function properly. Either there will be a performance penalty, which we called non-failure limitation, or the heat pipe might just fail. It will not transfer any heat. Okay, it might even get damaged, right? So those things are the failure limitations. So there are non-failure limitations and failure limitations. Okay. So the Q which you can transfer um, can be calculated based on this expression, right? So you can get something like this. So this is the maximum delta P that you can generate. So solving this, you can get Q. So that Q is this. All right. So sonic limit. Sonic limit is when you have high mass flow, you get high vapor velocity. So the flow in the core of the heat pipe can get choked, etc., etc. So again, here we are in no position to derive these expressions. So this will just calculate. Right? That 0.474 thing will just calculate in while solving problems. And there is also entrainment limit. Entrainment limit means, okay, you have the vapor going like this from evaporator to condenser, liquid moving in the opposite direction, right? So say there will be some effect of shear and the vapor might catch some liquid droplet. Okay, and then that is entrainment. Entrainment is basically that catching of the liquid by the vapor, and that's not desirable. No, you want only vapor to go to the condenser so that it can condense, right? So there are those issues. So the interaction between the counter current, liquid and vapor flow, they are going in opposite directions. So counter current. So there is that results in viscous shear forces, and the shear forces happen at the liquid vapor interface. So liquid at the bottom, vapor above it. So there is shear taking place, and because of that, entrainment takes place, and that that is problematic. Okay. So there are some calculations of this also, and there is also calculation of the vapor velocity. The vapor velocity can be calculated from the heat transfer, and it will also involve HFG. HFG is important because there is phase change taking place, right? So the heat transfer will be related to some mass flow rate and also the HFG, enthalpy of vaporization. So this you can figure out. This is easy to calculate. Okay. Now, this is the maximum heat transfer due to entrainment. All right. Now there is a boiling limitation also. So as I told you, beginning of the class, that sometimes boiling can also happen in the evaporator part. Okay. So this can happen if you have high heat fluxes. High heat fluxes, so nucleate boiling might occur in the wick structure. So vapor becomes trapped in the wick, and if you get vapor trapped in the wick is a porous structure, and you get vapor trapped in the wick, then that will prevent the liquid from flowing back. Now the liquid has to flow back also to the evaporator. So that can happen, and this one is obtained from some nucleate boiling considerations. So this is RCE, which you know, and there is an RN also. RN is the nucleation cavity radius. So nucleation, I hope you remember what is nucleate boiling, right? There are imperfections on the surface, and then there's because of, I mean, that those imperfection locations, those are nucleation sites. Nucleation happens, and then that starts off the nucleate boiling process. If you think about your undergraduate textbook, Incorporate and Divide, that has a chapter on boiling and condensation. So that's a nice chapter. So if you can read first few pages of this. You don't have to do that much actually, but if you want to understand this little better, then you can go to that part of discussion. Here I'm just pasting the formula there. That's all. Right. And there is also viscous limitation. So at low operating temperatures, the vapor pressure difference between the evaporator and condenser may be extremely small. Okay. So the viscous forces may be such that there is not a proper, so there's not enough pressure difference in the vapor basically, okay, between the evaporator and the condenser, and there is viscous effect. So the vapor will have a tough time moving to the condenser. Okay, so this is primarily a viscous effect, right? And this is a qualitative plot of these various limits at different temperatures. Qualitative because there are no numbers on the axes, right? So it tells you that this is how the boiling limit will look like. How are we showing the limits? We're plotting heat flow as a function of the operating temperature. Operating temperature means the heat pipe operates at some temperature. No, at some temperature there is liquid which is getting converted to vapor. Phase change is happening, right? So that sort of thing decides the operating temperature of the heat pipe. And the temperature of the heat pipe, if it is in this region, then the sonic limit is probably not very important. If it's here, then it's a viscous limit which is more important. Then the boiling limit will not happen. Things like that. This is the kind of interpretation. Okay. So what we'll do is, as you have understood by now, we have to primarily use all these relations and the overall physical learning to go to problems and try to solve this. Okay. Your job of somebody who has learned thermal design, who is learning thermal design, is to be able to design a heat pump. You know, let's say for a laptop, some heat dissipation from the CPU and all that is given, and you have some fan on the other side, on the condenser side, which will do the cooling. So some parameters are given. Now, how do you make that heat pipe? You know, what is the material of the body of the heat pipe? What is the wick material? What is the wick structure? And then what is the liquid that you take in the heat pipe, and what are the various dimensions? You know, these are the calculations that you have to do, right? And you have to make sure that what the parameter range which is given to you, performance doesn't degrade too much, and the heat pipe does not fail, right? So I'll ask you to read this for a couple of minutes. Okay, so nothing much in here. It just tells you what is the length of the evaporator, length of the condenser. Adiabatic section is 0.4 meter. Okay, and the diameter of the vapor space, which will come from here, that is 20.5 mm. And wicking structure has two meshes, two layers of 50 number mesh, copper screen. The screen is copper, right? And heat pipe operates at 80 degrees Celsius in horizontal position. Why is the position important? Because we saw that it can be inclined also. If it is inclined, then the calculation of the normal pressure drop and the axial pressure drop, this will change, because you have got the cos of psi or the sine of psi in those expressions. Okay, so you can calculate these things, because you can calculate the vapor pressure, temperature is mentioned. You can calculate HFG, you have the liquid density. These things you can all get from the back of the book, right? And these are some properties, mu of the vapor, mu of the liquid, and this is the surface tension number, okay? Surface tension coefficient, and this is wire thermal conductivity, right? So for what is 401? It's the value of the copper thermal conductivity, correct? And we will try to calculate delta PCM just from this 2 sigma by RC, as we know. We calculate this to be 492. And how do you get RCE? RC will come from the table. There was the table 3.1 that I had shown you, right? So that table will give you, for a particular type of wick, how to calculate the effective capillary radius. Remember effective capillary radius. You can just calculate that. And this is delta P of the vapor. This is these are some calculations which already discussed. So we get a delta P liquid, right? Delta P liquid was in terms of the heat transfer. If you change the heat transfer, delta P of the liquid will also change. This is delta P normal. And then you calculate things which the problem has asked you to do. So there is sonic limit, there is entrainment limit, all these calculations. And this is related to the boiling heat flux. This is an effective thermal conductivity of the wick, because the wick has meshes. So it has got these wires which are made of copper. So that's got one thermal conductivity. But there is also liquid thermal conductivity, because the wick is actually liquid, right? So the effective thermal conductivity that you will get will depend on the porosity of the wick, but it will also depend on the liquid thermal conductivity and the wire thermal conductivity, correct? So these things, and based on all this, you can calculate, okay, these are the various things, okay? All right, so we'll see this in more detail in the next class. I think today we have to stop because it's time. So this will all